In this final chapter, chapter 12, we're going to be discussing additional inferential procedures. Everything we do in this last chapter will all be in StackCrunch. So we'll be utilizing StackCrunch throughout this video. There are three tests that we're going to discuss. The first is called the goodness of fit test. We're going to look at a procedure that can be used to test hypotheses regarding a probability distribution. In other words, we will determine whether a set of data comes from a claimed distribution, either uniformly or varying probabilities. For example, we might want to test whether the distribution of M&M candies follows a certain color distribution, or we might want to claim a test whether the number of hits that a player gets in the next 4 at-bats follows a binomial distribution that has a probability of success of 29.8%. We're going to use the symbol chi-squared to represent the values of the chi-square distribution. This is similar to the z and t distribution, but looks a little different. We can find the critical values of the chi-square distribution in the table in the appendix of the book. Before we discuss how to read this, let's look at the characteristics of the chi-square distribution. First of all, it is not symmetric. Unlike the z and the t distribution, it is not symmetric. The shape of the chi-square distribution depends on the degrees of freedom, just like the t distribution does. As the number of degrees of freedom increases, in other words, as the sample size gets bigger, the chi-square becomes more closely related to symmetric. And all the values of the chi-squared are non-negative. Here's a picture of the chi-squared distribution. The chi-squared with 2 degrees of freedom, in other words, a really small sample size, is similarly to this the solid line here. As we get higher degrees of freedom or bigger and bigger sample, you'll see that it starts to become more and more symmetric. The graph starts to look more and more and more like a symmetrical curve. It kind of starts off with a skewed right graph, but as we increase our degrees of freedom, that skewed right starts to look more and more and more like the normal curve. Our hypothesis claims are always going to be the null hypothesis is that the distribution is as claimed. For example, if this was an M&M example, you would state yellow is 12%, green is 15%, blue is 20%, and so on. And the alternate would be, well, the distribution is not what we claimed. One of those probabilities might be different, or all. We're just simply stating all of the colors are not the same as what they were stated originally. So what can we do with this? We can conduct what's called a goodness of fit test. It's an inferential procedure that is used to determine whether frequency distribution follows a specific distribution. The idea behind this type of test is to compare the actual number of observations for each category with the number of observations we would expect if the null hypothesis were true. The null hypothesis is always going to be that all of the proportions of all of the different colors of M&Ms, for example, maybe are the same. This is an example of what we would use for a fair die. Suppose we wanted to test whether the dice was fair. So the null hypothesis in this case would be that all of the proportions are the same. In other words, each side of the dice has a 1/6 chance of happening. Now, if the die were not fair, for example, you would roll a 1 more often than others, maybe it's a weighted die, then clearly this claim would not be true. If a significant difference exists between the observed and what you would expect, we have evidence against the null hypothesis. The expected count for each category is the number of trials of the experiment times the probability of success in that particular category. Please note that a goodness of fit test are used to test hypotheses regarding the distribution of a variable based on a single population. If you wish to compare two or more populations, you're going to use a test that is presented in the next section, which we'll talk about in a moment. So we're only dealing with one population for the goodness of fit tests. There are a couple of conditions that must be met in order to conduct a goodness of fit test. All the frequencies are greater than or equal to 1, and no more than 20% of the expected frequencies are less than 5. We're going to conduct a test using StatCrunch, but if you want to see how the test statistic is computed, it is covered in your textbook in Chapter 12. The StatCrunch instructions First, we're going to enter the observed counts in the first column of your StatCrunch, and then we'll put what you would expect in the second column. Then to find the goodness of fit test, we go to the Stat, goodness of fit, and then highlight the Chi-squared test. Select the column that contains the observed and the column that contains the expected counts and calculate. So let's run through an example. In 2008, Malcolm Gladwell released his book called Outliers. In the book, Gladwell claims that more hockey players were born in January through March than in October through December. The following data shows the number of players selected in the 2010 National Hockey League draft according to their birth month. Is there evidence to suggest that the hockey players' birth dates are not uniformly distributed throughout the year using a 0.05 level of significance? You could tell by looking at this that there does seem to be more hockey players, in my sample at least, that were born in January through March than in the later half of the year. But is that enough? Is that frequency, that sample, large enough to determine that that is significantly different? So we're going to test this using StatCrunch. The first thing we need to do is we need to create our null and our alternate hypothesis. Our null hypothesis is that the birthdays are uniformly distributed. In other words, the birthdays from each of these quarters are the same. So the probability from the first quarter matches the probability of being born in the second quarter, which matches the probability of being born in the third quarter, which matches the proportion of those that are born in the fourth quarter. And if they are all the same, well, then that's going to equal, 25% for each quarter. Now, in the alternate, we're stating that the birthdays are not uniformly distributed. Or we could simply state that at least one of the proportions is different than the others. Those are saying the same thing. So then what we're going to do is we're now going to put all of this data into StatCrunch and perform the goodness of fit test. So let me switch over to StatCrunch. Okay, so what I did is I put the data that was from the table from our lecture notes into StatCrunch. You can see I put in the first column the birth months by quarter, and then in the second column I put those observed values. Now we do need to put in an extra column of what we would expect based on the proportion that we would expect if they were all equally likely. So the first thing I need to do is I need to add how many were in the observed column. So in my calculator, I'm going to add 63 plus 56 plus 28 plus 34, and that comes out to 181 hockey players. I would expect 25% of each of that 181 to be in each of those categories because all of those categories are of equal size. So I'm going to divide that by 4, and so that leaves me with 45.25 people that would be expected to have a birthday in each of those quarters. So I'm going to put equally likely outcomes of expected about 45 hockey players to be born in each of those categories, because we're assuming the probabilities of each quarter are equally likely. So then now that we have that information put in there, we're going to go up to stat and find the goodness of fit test. And then we're going to click on the chi-squared test. So here's where you select where your observed data is. Well, I titled it observed. See up here. And what we would expect is this evenly distributed expected column. Now, theoretically, I didn't have to create this expected column because there's also a link here that I could just say, just assume all the cells are of equal proportion, and it automatically knows that it would be 45.25 in each of those based on how many were in your observed column. So I could have just done that instead of creating this expected column. It would have done the same result. Now down here, I could click on all these additional things if you want to display the expected. In fact, why don't I just go ahead and display those here just so you can see what those look like. And I'll compute. And over here, you're going to see, let me pull it over to this, over towards my data. And over here, you're going to see that we had a total of 181 in our sample. Degrees of freedom of 3, because remember, we only have 4 data points, and degrees of freedom is always 1 less than. Our chi-squared value, this is our test statistic, which is similar to your Z or your T, which is 18.9. And we have a p-value, a really small p-value of 0.0003. So it again summarizes my observed and my expected results, and it also gives me this extra column called residuals. Residuals are the difference between the two. It's observed minus expected. So you could see in the first quarter and the third quarter, we were vastly different, our expected versus our observed. Okay, so there's our information. Those are our p-values. And now we've got to conclude our test. So let's switch back over to our notes. Okay, so now that we have our null and our alternate hypothesis, we already know our chi-squared value. Our chi-squared value, it was going to be 18.9 that was rounded, which resulted in a p-value of 0.0003. Now what we do is we compare that p-value to our alpha. We were asked to use a 0.05 level of significance. So our p-value is definitely less than our level of significance, which means we're going to reject the null hypothesis. If we reject this null hypothesis, we then can claim our alternate, which is that the birthdays are not uniformly distributed for hockey players. At least one of these quarters is different than the others. So the first, second, and third quarter could have been the same, but the fourth quarter could be vastly different, or all of them could be vastly different. It doesn't specify which particular proportion is different than the others. It's simply just saying they're not uniformly distributed. So one of them is going to be different than the others, at least. So in an interpretation, I would say that there is sufficient evidence at the 0.05 level of significance to conclude, and this is where you conclude your alternate. So we're going to conclude this information here. To conclude that hockey players are born not evenly distributed throughout the year. Okay, so that's the the goodness of fit test. Remember, you're using one population, in this case was hockey players, and you're comparing the proportions or probabilities of one characteristic but happening over multiple time spans. So let's do one more example of the goodness of fit test. This is using the M&M example that we started going over back. I think we started this in chapter 8. So if you remember, according to Mars, which is the maker of M&M candies, the color distribution for plain chocolate M&Ms is 13% brown, 13 red, 14 yellow, 24 blue, 20 orange, and 16 green. And that is the claim that the company Mars made, that they try to get into every single bag. Clearly, every sample is not going to have that exact distribution, but that is their claim, their goal to have. So we're going to find the M&M distribution, color distribution from our chapter 8 sample. We'll write those results in here, and then we'll use this information as evidence to claim that that is or is not true. So if you remember back from chapter 8, these were my results. You might have different results based on your sample, but this is what I had in my bag of M&Ms. Again, our null hypothesis is that M&M colors follow a particular distribution, which was 13% brown, 13% red, 14% yellow, 24% blue, 20% orange, and 16% green. Okay? So that is my null hypothesis. My alternate hypothesis is that the M&M colors do not follow this claim. So I'm not stating that any one particular color is the reason that it doesn't follow the claim, but at least one of the colors is definitely different. Okay, so we're going to use that information. We're actually going to go over to StatCrunch, and we're going to enter in all of this observed data, and then we'll also enter in our expected data. So this is our observed, and then we'll also go back and do our expected. And I'll show you how to do that when we get over to Excel. Actually, why don't I do it on paper here first? So if this is our observed, this is what we observed in our bag. We also are going to have to create an expected column, and we have to figure out how many total M&Ms there were. Let me add these up. I believe there's 54, but let me add them up to be safe. Yes, 54. All right, so there was a total, the sum is 54 total M&Ms in my bag. So to find the expected number in each, they're not all equally likely, because remember, they claimed that they follow a particular distribution. So we're going to have to figure out what each of those percentages of 54 is to find out what we would expect. We expect to have 13% red in every bag. So 13% of 54 is going to be 7.02. Yellow, we expect to have 14%. So 14% of 54 is 7.56. We expect 24% blue, which is 12.56 out of the bag of 54 we would expect to be blue. Green, we expect there to be 16% green. So 16% of 54 is 8.64. You get the idea. So then we have 10.8 and 7.02. Obviously, if I add all of those up, I'm going to get 54 as well. So these are going to be the columns that StatCrunch is going to require in order to perform the goodness of fit test. It's going to compare this distribution against this distribution, and it's going to determine whether those are the same or is at least one of those rows different than the others? Okay, so I switched over to StatCrunch, and you can see I already entered in everything that was in our table. I've got the colors on the left, I've got the observed values and the expected values. So then again, we perform the goodness of fit test, which is under our stat, and we need the chi-squared test. Obviously, our observed is going to be in the title called observed, and we have to make sure that we select the expected column here because they are not all of equal proportion like they were in the previous example. So let me go ahead and compute, and it gives us our observed and our expected here, and also it gives us our chi-squared and our p-value. So I'm going to write that down in my lecture notes, and I'm going to go over to my lecture notes now, and we'll finish the rest of this problem based on a p-value of 0.06. Okay, so from StatCrunch, we found that our chi-squared test statistic was 10.49 with a p-value of 0.0626. Now, in the problem, it stated that we were using an alpha of 0.05, and you can see that my p-value is definitely larger than my alpha, which means we're going to fail to reject the null hypothesis. So remember my null hypothesis was that the M&M colors follow this particular distribution, and we have failed to reject that. So it's not that we necessarily agree that this claim is true, it's just that my sample, my small little bag of 54 M&Ms wasn't enough information, or in other words, the distribution might not have been unique enough as evidence to say, I don't agree with this. It's just not enough evidence. So in my description down here, I would state that we have insufficient evidence at the 0.05 level of significance and this is where we can to conclude our alternate, to conclude that M&M colors do not follow the Mars distribution that was claimed. Okay. Okay, so now we're going to move on to the second test for this chapter, which is called the chi-squared test of independence, and then we're going to do a chi-squared test for homogeneity of proportions. So the chi-squared test first for independence is used to determine whether there's an association between a variable and a column variable in a contingency table. In other words, there's going to be one population with two separate characteristics, and the test will determine whether those two characteristics are dependent or independent. It's essentially a hypothesis test with a specific null and alternate. A couple of the conditions that must be met for the chi-squared test for independence is that all the frequencies have to be greater than or equal to 1, and no more than 20% of the expected frequencies are less than 5. Your null hypothesis states that variable 1 and variable 2 are independent, and your null will be that they are dependent. And we'll go over an example in a minute. The StatCrunch instructions for doing this is you're going to enter the row variables in variable 1 and enter the data for each row in variables 2, 3, and 4, and etc. And then we'll do stat tables, contingency tables with summary. So when we get to that in just a minute, we're going to look at first an example, and we'll put this into StatCrunch. So the example that we have here says that an obstetrician wants to learn whether the amount of prenatal care and the wantedness of a pregnancy are associated. So he randomly selects 939 women who had recently given birth and asked them to disclose whether their pregnancy was intended, unintended, or mistimed. In addition, they were to disclose when they had started receiving prenatal care, if ever. The results of the survey are as follows. So here we have our first variable, which is the wantedness of the pregnancy. Was it intended pregnancy? Was it unintended? Or was it just mistimed? And then across the top is our second variable as to when they started receiving prenatal care. Did they start seeing the doctor as early as from 0 to 3 months, from 3 to 5 months, or not till 5+ months, or if ever? And all of the observed data is in this contingency table, with the first characteristic in the first column and the other characteristic is across the first row. So let's first describe our alternate and our null and our alternate hypothesis. Our null hypothesis is that the two variables are independent. In other words, wantedness and prenatal care are in fact independent. Independent means that one has nothing to do with the others. In other words, if regardless of if you wanted or unwanted, your pregnancy has no bearing or prediction as to when you received medical attention. And the alternate then is going to be that they are dependent. In other words, the two variables are dependent. In other words, if you know whether the pregnancy was intended or not intended, you can forecast whether that woman had received care early or late. So I am going to switch over to StatCrunch and compute this contingency table and do the chi-squared test for independence in StatCrunch. Okay, so you're going to see that I already went ahead and entered all of the information into StatCrunch. In the first column, I'd put the row headers, which is the wantedness of the pregnancy. And then across the top, I put the second characteristic, which was the timing in which they sought out prenatal care. So this is my contingency table. Now I'm going to go to Stat, Tables, Contingency Tables, and with Summary. So in the first thing, it says to select the column variables. So the column variables are going to be these columns here. And I'm going to select them all. The row labels are in the first column called wantedness. So these are the row labels, which is the characteristic of wantedness. And then the columns is going to be your second variable over here. And then make sure to check expected counts down here. And also I'm going to turn on the contributions to the chi-squared, just so you can see what that is as well. So let me go ahead and compute this. Okay, so now let's go over this table. The first thing you're going to notice at the very bottom, those are the results. That's what we're going to use in order to perform our test. So we have a chi-squared value, a test statistic of 21.26, and a p-value, very small p-value of 0.0003. But also in the rest of this table, you're going to see some other information. In the first value is going to be the count. So this is how many we observed, and that matches what we have in our contingency table. The next value is going to be the expected count. So we would expect 573 women to have fallen into this category, but instead we observed 593. So this is the observed, and this is what was expected. Now the third value is going to be the contributions to the chi-squared test. So you want to look for the biggest value. Okay, the biggest value you're going to find is under the unintended pregnancy and prenatal care that was 5+ months. So this value right here, the 6.21 or 6.12, this value right there, this is the value that contributed the most into making the decision. Remember, this decision, since the p-value is so small, definitely less than alpha, which means we're going to reject the null hypothesis, meaning that the two variables are in fact dependent on one another. And the item that had the most contribution to making this decision are the women who had an unintended pregnancy who waited until 5+ months to receive prenatal care. And that's based on the number, the highest number in the contributions field. Clearly, there were others. This is also a big number, another big contribution also over here. Okay, but the biggest one was the women that fell under this category. So let's switch back to the notes and summarize everything that we have found. Okay, so let's recall our p-value. Our p-value that we found in StatCrunch was 0.0003, which is indeed less than alpha, which means we will reject our null hypothesis and we will claim that wantedness and prenatal care are in fact dependent on each other. So we would state that there is sufficient evidence at the 0.05 level of significance to conclude, and this is where you put in your alternate, that wantedness and prenatal care are in fact dependent. Okay. So for the last question, I'm asking you to compare the observed frequencies with the expected frequencies that we did in StatCrunch. And I'm asking which cell contributed the most to this test statistic or making this decision. And we decided that the women, the cell that contributed most, were those that had an unintended pregnancy and those that waited prenatal care after 5 or plus months. More people with unintended pregnancies wait a long time to get care. The last test that I have for you is called the chi-square test for homogeneity of proportions. In this test, whether separate populations have the same proportion with one characteristic. So for this one, you have multiple populations with one characteristic, which is unlike the test for independence that we just did, which was one population with two characteristics. But this is going to be done the very similar way with using these contingency tables. So the data is found by randomly sampling each population separately and then determining if each subgroup is homogeneous of the other. The procedure is identical to the test of independence that we just did. The StatCrunch instructions from the previous page can also be used. So our null hypothesis is that the proportions from these multiple populations is the same, And then your alternate is that at least one of them is different than the other. And we don't specify which one, we just know at least one. So as an example, in a recent survey conducted by the Pew Research Center for the People and Press, a random sample of adults of 18 years and older living in the continental United States was asked their reaction to the word socialism. In addition, the individuals were asked to disclose which political party they most associate with. Results of the survey are given in the table. Does the evidence suggest that a different proportion of individuals within each political affiliation reacts positively to the word socialism? So we have three populations: Democrats, Independents, and Republicans, and we just have one characteristic, which was their reaction to the word socialism, whether they reacted positively or negatively. You could see that Democrats seem to be pretty 50-50 on the positive versus negative views, but the Independents and the Republicans tend to think negatively about the word socialism. So there does seem to be a difference maybe with the Democrats than there are with the Independents and Republicans at a first glance. But in order to determine whether it's statistically significantly different, we have to run the hypothesis test. So the first thing we always do is we come up with our null and our alternate hypothesis. The null is that the proportions of each political group are equal. So the proportion of Democrats that feel positively about socialism is equal to the proportion of independents, which is equal to the proportion of Republicans. Our alternate is that at least one proportion is different. So now we're going to run over to our StatCrunch and do this one final calculation using the same table, contingency table, that we did for the chi-squared test for independence. Okay, so I went ahead and put the contingency table into StatCrunch. Again, we put in the first column, we put the first the one and only characteristic, which was whether they thought positively or negatively. And then across the top is the different populations from which we asked the question. So recall we go to Stat Tables, Contingency Tables with Summary, and we're going to perform this contingency table test. So the columns are located in the Democrat, Independent, and Republican categories, and those are our populations, and they were asked what their thoughts were on socialism. So again, I'm going to go ahead and give the expected and the contributions here, and you leave this as the chi-squared test for independence. We don't change that. We use the exact same test that we do for independence. Don't use these other ones here. And then we compute. Okay, so over here, let me slide it over. Okay, you see our contingency results. We have an observed Democrats that thought positively of 220, but we would expect only 145 if these were all to be of equal proportions. And it gives us our contribution right here. So you can see that we have a very, very small p-value, which certainly means we would reject the null hypothesis, which was that the proportion of each political group are equal. So we're going to claim that at least one of these proportions is different than the others. And if I were to guess, I would assume that again, it is Democrats that are different than the others if they're not all different, because they have the highest contribution into making this decision. So let me switch back over to the notes to make our final thoughts and our final interpretation. Okay, so recall that our p-value from StatCrunch was less than 0.0001, which is certainly less than the alpha that we were asked to use for our level of significance, which means we will reject the null hypothesis. So we're going to state that at least one of the proportions is in fact different than the others. We haven't specified which one, but we can make a good assumption that, again, the Democrats are at least different since they had the largest contribution. So we will state that there is sufficient evidence at the 0.05 level of significance to conclude there is a difference in the proportion of individuals who react positively to the word socialism. We also know that Democrats who react positively contributed the most to this decision. Now, on the following pages, there are many examples that I would suggest you go through. I'm not going to do those in the video, but I would suggest that you try these on your own. There are 6 of them, and we've just learned 3 different types of tests. I do believe there's 2 of each. So the hardest part, I think, of this chapter is deciding what test to use and what type of example this is, so you can use the appropriate test. So I'm going to leave the next 6 problems for you to try on your own. The first thing you need to do is decide and determine what type of test you're going to use. Is it goodness of fit? Is it chi-square test for independence? Or is it the chi-square test for homogeneity? Decide on the test. Once you think you know what kind of test it is, go ahead and perform it. I do have the answer keys that are going to be posted for these that you can compare later. But I think it's a good a tool to try to figure out on your own which test you would use for each of the following questions.